Okay, so you may say, what are the gas laws? We talked about ideal gases and real gases, and we talked about ideal gases are the perfect gas that would follow the gas laws perfectly, mathematically, and have predictable mathematical outcomes and values. However, so what are the gas laws? And the first one we're going to look at is Boyle's law. And scientists knew a lot about these laws intuitively beforehand. But again, Boyle gets the credit for this because of some of the experiments. So basically, Boyle's law looks at the volume and the pressure of the gas and how they interact. However, when we study Boyle's law, we're going to leave the temperature constant. All right, so that means you're going to do these without changing the temperature of the gas at all. So think about playing around with the temperature, with the volume and the pressure of a balloon in a lab room or in a room where you're just at a constant temperature. All right, so we're going to assume that the temperature is constant in this case. All right, so let's just think about this a little bit. So what happens is we're going to talk about the volume, and we're going to find out that the volume of a gas, okay, the volume, the space that the gas takes up, varies inversely with pressure. Okay, which means as one goes up, the other goes down. As one goes down, the other one goes up. Now, why is this the case? Well, if you increase the pressure on a gas, okay, what you're essentially doing is limiting the space, or you're reducing the space in between the gas particles. So if you have two gas particles here, you're going to end up bringing them together, okay, and that would cause the volume to go down. So if you increase the pressure between the gas particles, you're going to lower the volume or limit the space between them. You're going to bring them closer together, and that causes the gas to take up a less volume. But it does this in a proportion. Okay, so just to illustrate this a little bit, if we take some pressure volume data of a gas, so let's just say we have the volume, let's say the volume is in liters here, and the pressure is in millimeters of mercury. All right, and we take these values, and we take 240 of a pressure and 1.8, okay, and we begin to reduce the pressure. So you can see as we go along here, we're getting less pressure. So as you reduce that pressure, we're going to allow that gas to expand. And you can see the volume of the gas becomes greater as that pressure is reduced. So you have this, as the pressure is going down, you can see the volume is actually going up and so on. If you go backwards, you can see the same thing. As you increase the pressure, you will see the volume go down. Now, something interesting happens with this law, this rule. I mean, this general idea. If you take the pressure times the volume, so let's take P times V for some of these. We'll go 240 times 1.8, okay, and we'll get 432. Okay, this would be 400. Okay, 160 times 2.5 would be 400. Okay, again, we can probably kind of pick out the 400s. 400, 420, 400, 400. And again, it's experiments. So you're not expecting everything to be perfect all the time. You shouldn't expect that. Okay, times 3.2. Okay, 120 times 3.2 is 384. Okay, so generally speaking, if you take a look at this, you're going to really see that anytime you take the pressure times the volume, you always equal this constant number. Okay, and so really, the conditions of gas can change, and you can manipulate this gas and change anything you want. But notice how it always equals out when you do the pressure times the volume. Now, it is equals to the same number. That's going to be something interesting where you can use this as a prediction. All right, so we're going to go over to our graph. If we were to graph the volume and the pressure on the bottom, we would get this. If we would graph these numbers, and I graph this, you can see it has this inverse curve that tends to low down. So as the pressure is increasing, right, your volume decreases. All right, now if we pick any 2 points on the graph, let's just pick point one being this point here and being this point here. Again, we're going to notice that your product of the two is the same, right? We're going to get the same number, which is going to be 400. Now, this just the 400 doesn't have to be for every gas. This just happens to be for our measurements here. Okay, so really what we can do is that means that P times V equals a constant. So we really could say that the pressure times the volume at one instance is going to be equal to the pressure times the volume at any other instance. All right, and that becomes Boyle's law. So really, why is this good? Well, in a way, if we know the pressure and we know the volume at one instance, and we know the pressure at the second instance, if we want to change it to something new, then we can figure out what volume that's going to be. We can predict this. All right, so you can use this as a prediction because we know that pressure times the volume is always the pressure times the volume in any other instance. All right, so that becomes Boyle's law. Okay, so a couple of other things about Boyle's law that we see in real life, and then we'll do a little mini calculation. Pushing the plunger, okay, of a which is increasing the pressure of a plugged up syringe, decreases the volume of the trapped air. Okay, so again, any syringe. So if you have this a little plunger on a syringe, and and here's the volume. If you lower this, you will lower the pressure, and so you increase the pressure by pushing down on this thing. You will lower the volume of the space inside. Okay, breathing is important too. As you increase the volume of your lungs, when you breathe, you bring your diaphragm down. That increases the volume of your lungs. If you increase the volume of your lungs, the pressure in your lungs will drop, allowing air to be pulled in from the outside. Again, lower pressure in the lungs, higher pressure outside in the atmosphere allows you to breathe. Okay, so you can see as we compress this gas under increasing amounts of pressure, if we double the pressure, if we half the pressure here, okay, or actually if we double the pressure here, we end up halving the volume. All right, so that's important to know that this is proportional as we go. All right. All right, so since PV is a constant, we can say that PV P times V or equals P2 times V2. So this is the initial conditions beforehand, and this is conditions after. Okay, so let's just say we have a 40 ml sample of gas, and it's in a syringe at 760 millimeters of mercury. Okay, what is the final volume? So they're asking you for the final volume. So that's going to be V2. So we have V1 here, we have P1 here, okay, and we're looking for V2 if the volume of the gas is placed under a new pressure. So your new pressure is going to be P2 here. So we're going to say P1 V1 equals P2 times V2. Okay, we're going to say V1 is going to be 40 milliliters. We'll say P1 is going to be 760 millimeters of mercury. Okay, and then we're going to set that equal to the pressure is 920 millimeters of Hg, okay, times our x. Okay, and if we work that out, we cross multiply, or we figure out our x, we're going to find that x is equal to 33 milliliters. Something you want to keep in mind, you want to make sure that your units are the same on both sides. If you're dealing with pressure units on this side, they should match, and your milliliters should match. If you're using liters or milliliters, just make sure they match on both sides. Okay. Another thing I want you to do, make sure this makes sense. Does it make sense that you have a lower volume than you started with? Well, let's take a look. If you started with 760 and you increase the pressure of the gas, okay, on the pressure on the gas, and you've squished it or you've pushed it down a little bit, the syringe, you would expect the 40 milliliters to take up less space. And in fact, it does. So that looks like a reasonable answer. Okay. So that's Boyle's law. Okay. Next one we want to think about is something called Charles' law. Okay. And again, we're looking at these ideas of taking a PV and T, like these values PV and T. Okay. This PVT thing, we're just going to exchange these values. So Boyle's law had the temperature constant. Well, in Charles' law, we're going to keep the pressure constant. So we're going to play around with the gas with its temperature and its volume. So the volume of a gas is going to increase, is going to vary directly with the temperature. So here we have the situation where I like to call this the balloon law or the expanding law, where we know things expand with temperature. We know a gas is going to start to expand or it's going to blow out with increasing temperature. All right. And we're going to worry about the pressure becoming constant. So we're not going to worry about that. So why is this the case? Well, when you increase the temperature, you increase the kinetic energy of the particles, okay, which is your speed, right? Your motion of your particles. Okay. So when you increase the speed of the gas particles, you're going to cause them to want to spread out. And as they want to move out, they're going to put pressure on the walls of the container. And if the container is allowed to expand, this is going to expand, but it expands proportionally. So if we graph the volume and the temperature, again, you want to know your graphs by heart. All right. If we expand this, okay, and we look at the graph on this, we're going to see that we get this straight line graph for volume and temperature. Okay. As the temperature increases of the gas, so does the volume. In fact, if you increase it by twice, you get twice the volume. Okay. So it's really different than Boyle's because it's not opposite, it's the same, it's this straight relationship. Okay, so in this case, the volume times the temperature is, I'm sorry, the volume divided by the temperature is going to be constant. Again, before we had P times V, this is V over T. Let's prove it. If we pick 2 points on the graph and we look at 66 and T, we're going to find out that 66, we take 66 and we divide it by 100, okay, we're going to get 0.66 if we divide V over T, okay? And if we take 100 and we divide that by 300, it should be 200. Sorry, 200, guys. This is 200 here. If we take 200 and we divide that by 300, okay, again, we're going to get 0.66. So this number should be 200 here. Okay, we're going to V divided by T, we're going to get 0.66 again. So again, any points on the graph that you would choose here would be that point. So important to know that we're looking at the right, data here. So if we take a look, so again, that's going to be the case. So V over T is going to be the same number. Okay, V over T equals a constant. All right, and we looked, so a couple of things that we're going to see with some real life examples with this. If I get my pen going. Okay, a fully inflated balloon is going to, so if your balloon is large, a fully inflated balloon like that, if you bring it out on a freezing cold day, again, this is going to take up less volume. It's going to shrink, right? It's going to go from a volume of some point, and when you bring it on a cold day, it's probably going to shrink into a smaller volume. Okay, heated air in a hot air balloon is going to expand, which inflates the balloon. Again, so this is like the balloon law almost. All right, so since the Vt is a constant, V over T, we can set up our expression as Charles' law, being V1 over T1 is V2 over T2. And again, you can see boiling water, which is hot, is going to produce a large volume. And when you cool it down, you're going to get this lower volume. Okay, so you have a high volume here in hot, lower volume there. Okay, and again, a little pictorial view of Charles' law, where if you start with 100, okay, and you double the temperature, you will also double the volume. Okay, so each time you do this, so you will double the volume each time you go. Okay, so it's important to know. So a 3.6 liter birthday balloon is at 25 Celsius. This is a constant pressure. Again, constant pressure means we're not changing it. What is the new volume if the balloon is brought out outside on a cold day? Okay, one thing you want to remember with Charles' law is when you're dealing with temperature, T must be in Kelvin. Can't underestimate that enough. So really important that you stay in Kelvin. So we have V1 over T1 equals V2 over T2. Okay, our volume is going to starting with 3.6 liters. Okay, now important, we given Celsius here. We have to make sure we take 25 and add it to 273. Don't forget. Okay, degrees Celsius, sorry, Kelvin is equal to your degrees Celsius plus 273. Don't forget our conversion. Okay, and we set that equal to, what is the new volume? I don't know. It's going to be over 0. Be careful here. You don't want to put 0 in the denominator. It's one of the reasons why we use Kelvin. Okay, we're going to want to make 273 here, Kelvin. Okay, so if I cross multiply, again, I want to make sure I add that together first, which is going to be 298 Kelvin. Okay, if I do this, I end up with 3.3 liters. So if I'm at room temperature and I go down to 0, my 3.6 liter balloon should get smaller because it's getting colder. It should sit less volume. 3.3 liters would be the volume. All right, so important stuff here. Just make sure you know exactly what's going on. All right, and make sure you realize what and the important concepts between the two. The next law we'll look at in the next video.